Welcome back everyone. In this lecture actually I will continue with more representation theory because we still haven't defined some of the important objects that one can actually create in the representation theory. So, before that I will actually recall what we were doing in the last lecture. Okay, I made a very simple calculation mistake. I will rectify that now. So, we defined characters for this SL2 representations. So, if you recall, so what is character? So, you start with V being finite dimensional representation of SL2C. So, we talked about H character. So, we are simply just a character. So, the character of V is defined to be, you write V first of all direct sum of V gamma, where gamma coming from Z, where V gamma is nothing but the gamma eigenspace. Okay, those vector in V such that HV is nothing but gamma V. So, then so the character of V actually keep tracks of which gamma appear here in this eigenvalues and as well as the dimension of this V gammas. So, in particularly, so this is the character of V is the sum of dimension V gamma times x power gamma, where gamma is coming from Z. And it is a fact that this is actually element of the Laurent polynomial ring. Okay. So, one can actually restrict to Z, not a problem, but as well as you can see that one can think it as a element of this Laurent polynomials over complex numbers as well. So, then we try to actually compute what is the character of this VD. So, I wanted to actually simplify that. So, let me again do it. So, if I take this character of this VD, where VD is a given finite dimensional irreducible representation. Okay. So, then we know that this VD has this basis. So, the VD has this basis V naught etcetera VD and the corresponding H eigenvalues will be D. Okay, let me write some more terms. So, this is V naught V1 etcetera VD minus 1 VD. So, then the corresponding eigenvalues will be V naught will have D, V1 will have D minus 2 and so on, minus D plus 2 and then minus D. So, these are all the H eigenvalues of these eigenvectors V naught etcetera VD, which is of basis of capital VD. So, then it is clear that the character of VD is nothing but, because all these eigenspaces are one dimensional. So, this character of VD is nothing but x power D plus x power D minus 2 plus etcetera plus x power minus D plus 2 plus x power minus D. So, in particularly what we can do, we can take out x power minus D, that is what we did last time also. The character of VD becomes x power minus D times x power 2D plus x power 2D minus 2. So, this is t minus 1 plus etcetera plus x square plus 1. Okay. So, that is what we got. So, now recall the formula that x power minus 1 divided by x minus 1 is given to be 1 plus etcetera plus x power n minus 1. So, now using this identity we can again simplify this character of VD. So, if you simplify further, then what do you get? This is x power minus d times, so x power 2d minus 1 divided by x square minus 1. So, you put x square to be y, then this is what you get. Okay. So, now you can see that, so this is same as equal to character of VD. So, this is equal to x power d minus x power minus d divided by x square minus 1. So, now you multiply and divided by x power minus 1 both sides. So, in the numerator and the denominator, then what do you get? You get it is exactly equal to x power d minus 1 minus sorry. So, here, so this is starting with x power 2d. So, this has to be plus. Okay. So, I made a mistake. So, let me just rewrite. So, this is going to be x power 2d plus 1 minus 1 divided by x square minus 1. So, if you multiply by x power minus d, then this is x power d plus 2 minus x power minus d. So, divided by x square minus 1. So, now you multiply by x power minus 1 and then divide by x power minus 1, then we get x power character of V d to be x power d plus 1 minus x power minus d plus 1 divided by x minus x inverse. Okay. So, this is somewhat some better form of writing. The character of V power d is nothing but x power d plus 1 minus x power minus d plus 1 divided by x minus x 1. So, later this kind of expressions will appear in many places. Okay. So, these are all actually kind of quantum integers, but anyway let us not get into that. So, but the character of V d, it has some very nice formula like this. So, that is where I stopped last time. So, now what we do, we will continue with the SL2 representation theory, and then we will see like so what will be the procedure to decompose given 5-dimensional representation into smaller or irreducible 5-dimensional representation of SL2. Okay. So, for that we start with let us say V, which is a 5-dimensional representation of SL2C. So, if you think about it, suppose if you can write already V as some direct sum of this irreducible representation. So, then what you can do, you can actually group all the representation, they are isomorphic. Okay. So, then each irreducible representation will appear in the decomposition of V with respect to some multiplicity. For example, that multiplicity you can get it from by computing the character. Okay. So, first you write some V d1 and let us say this appears n1 times. So, this is the notation. So, this means, so V of d direct sum some n means just V of d direct sum n number of times. So, here n number of times we are adding. So, if you use this notation, then it is clear that using Weyl's theorem, this V can be written as V of d1 direct sum n1 direct sum etc. direct sum V of some dr direct sum nr. So, we have grouped isomorphic copies. So, that means we can assume that this d1 and dr all are distinct. So, since we are talking about this non-negative integers, so we can order them so that we can assume that d1 is bigger than etc. bigger than dr. So, it is in the decreasing order. Okay. So, this is the assumption that we can make. So, in particularly if we compute the character of V will be exactly equal to n1 times the character of V d1 plus etc. plus nr times character of V dr. Okay. So, this is what we get. So, now if you think about it, how are we going to get the top component? Okay. So, once we actually understand how to pick this top components, so then it is more or less clear how you go about picking the other components. Okay. So, for that, so let us look at what is really happening here in this decomposition. Okay. If I take this copy of this V d1, so then you can see that, so there will be just some copies here, okay, V d1 etc. V d1. So, then each copy actually will contribute to H eigenspaces. So, even though eigenspaces of V d's are one dimensional, but we have taken multiple copies of them. So, even not only that, so there are some contribution that can occur from some VD lower than this D1 also. Okay. So, in particularly what I am trying to say, if you look at this capital V and then if you look at some gamma, the gamma eigenspace, okay, H eigenspace of this V, then you get contribution of this gamma eigenspace from all these VDIs. Okay. So, now these gammas, because they are all coming from the eigenvalues of these VDIs, and these VDS in some sense they are all ordered. Okay. You can see that first we have written VD1 and then we have written VD2 and so on, we have written VDR. So, they are all in the decreasing order. But if you focus on only this VD1 etc. VDN, so how it looks like? So, it looks like, so the D1 space, okay, for example, it will have all one dimensional. Okay. So, then depending upon the number of copies, so you will get that many one dimensional D1 eigenspaces. Okay. So, corresponding to D1 eigenvalue. So, now, so this is how many copies are there? There are n 1 copies. So, that many things that we will have. So, for simplicity let us assume r equal to 2. So, I will try to explain what is happening in r equal to 2, that more or less explains everything else. So, now if you go to VD2, so then what will happen? So, this D1 definitely greater than D2. So, the D2 will appear somewhere here. Okay. So, this D2 will be here. So, this is VD2 and so on VD2. So, this is how many copies? There are n 2 copies of them. Okay. So, now if you think about it, this VD1 will actually contribute something like this. So, I can actually represent it using this rectangle. So, where the first box corresponding to eigenvalues D1. So, those are all the top eigenspaces, okay, inside this VD1 etc. VD1. So, now each box will contribute to one dimensional eigenspace for the VD1. So, this is VD1. Now, what will be the next? The next one will be VD1 minus 2. So, that will be just below this. So, that is just again you will get n1 copies of that D1 minus 2. So, then you can go and so on, then you reach VD minus 1. So, then this will be the least eigenvalue because this D1 is max. So, minus D1 will be the minimum. So, that will give you some box here. Okay. So, this is will be your corresponding to minus D1. Now, if you go to VD2 etc. VD2, so D2 will appear somewhere in the below D1, okay, wherever it is does not matter. For example, if D2 can be obtained from D1 by subtracting this even number, so then this D2 will match with one of this D1 minus 2i. Okay. So, in that case it will actually match with this box here. So, let us say this is D1 minus 2i. Okay. So, in case D1 minus 2i is equal to D2, then whatever we are getting here, it will match up with this. Okay. Similarly, so then it will go all the way up to only that minus D2, okay, like this. So, this will be like minus D2. So, each copies is going to give us, so this one column, and then if you read it from the row, so then we will be able to calculate the dimension of this D1 minus 2i dimensional eigenspace. Of course, this picture is true only for when D2 is obtained from D1 by subtracting some even number. If this is not the case, then what will happen? The picture will look something like this. You will have first this D1 etc. D1, okay, something like this. So, this is how the D1 copies will look. So, this is D1 and this is D1 minus 2 and this is minus D1 and so on. So, this is VD1 and then this is VD1 and there are N1 copies. So, now let us say D1 minus 2i is not equal to D2. So, that means the parity differs. If the parity differs, so it is not going to be exactly hitting this D1 minus 2i. So, then what will happen? So, basically there is a mismatch. So, when you take that D2, so D2 will lie somewhere here, okay, but it will not contribute to that values of this D1 minus 2i. So, but it will just stay here, okay, but they are all having different parities. Okay, this is VD2, VD2 and here you have N2 copies, okay, and then here this is the D2 and then this is minus D2 and then you go like D2 minus 2 and so on and then minus D2 plus D2. So, there will not be any, like these two figures cannot match like here, okay, here this is matching, okay, but here it cannot match. So, then you can see that the contribution of the D2 dimensional the contribution of D2 eigenspace inside capital V will be same as just this N2 copies, okay, D2. So, this is like what we are observing. For example, if you are interested in picking up, okay, the top component VD1, so then all you need to do is just calculate the dimension of VD1. Okay. So, the number of copies N1 is going to be dimension of VD1. So, now what will be the number of copies VD2, okay, VD2. So, in case if there is a matching, okay, so that means D1 minus 2i is becoming equal to D2. So, then there is a contribution of this D1 minus 2i, that eigenspace coming from this VD1 etc. VDN, and similarly contribution again there is another contribution here, okay, coming from this VD2 etc. VD2. So, that means the dimension of VD2 will become exactly equal to N1 plus N2. Okay. This is in case D1 minus 2i is equal to D2. So, then how do you recover N2? So, you just recover it by subtracting VD2 from VD1. Okay. So, now what happens if they do not match? So, in case if they do not match, if D1 minus 2i is not equal to D2. So, this is equivalent to saying D1 is not concurrent to D2 modulo 2. So, in this case we will not have any contribution for this VD2 from this copies of VD1. Okay. So, in this case you can see that there is no contribution of VD1 in the eigenspace v power d2. Okay. So, that means n2 will exactly be equal to dimension of Vd2. Okay. So, this is how you recover. So, by knowing what will be the parity match and so on. So, this is actually you can repeat for other copies as well. Okay. So, in case if you are interested in capturing the topmost copy, so then what you do, you just compute the dimension of this D1 eigenspace, okay, H eigenspace. So, corresponding to the eigenvalue D1. So, that is this. So, then the dimension of that will give you exactly how many copies are there. So, when you come to D2, you need to be careful. Sometimes this D2 can be equal to D1 minus 2i. In that case, you have to subtract this dimension of D1 from the dimension of D1. Sorry, this is not dimension of D1, so which is exactly N1. Yeah. So, in case, so this is just N1 from this dimension of VD2. Okay, because N1 plus N2 will give you the dimension of V D1 minus 2i, which is D2. But if there is no matching, like that means the parities are different, then just a dimension of VD2 will give you just N2. Okay. So, now it is clear like how to get these number of components from by knowing the dimension of these H eigenspaces of capital V. Sometimes that is easy to calculate. Okay. In some sense, that is what we are recording inside the character V. Okay. So, character V contains all this data. So, this contains all these data that we are talking about, that we needed to recover the multiplicities. Those ni's are called multiplicities. Okay. DDI inside capital V. So, this is very important observation. Okay. This observation is actually telling us how to decompose given capital V, knowing the character, how to decompose capital V into direct sum of this irreducible representations. So, now like to get more hand on this, one should actually do lots of examples. Okay. Maybe I will leave it to you to check one of the important example. Okay. So, I leave it as exercise, maybe you can do the calculation and then see what happens. So, SL2C, so naturally sits inside SL3C. Okay. So, how it sits, you can take it to be this 3 by 3 matrices and then take star 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 and then 0 0 elsewhere. Okay. So, this is sitting inside SL3C and it is naturally isomorphic to SL2C. So, in particularly using this natural identification, you can make SL2 act on SL3. Okay. So, in particularly this is finite dimensional SL2 module. So, you can try to compute what will be the decomposition of this finite dimensional module. So, compute the decomposition of SL3. Okay. Treat it as SL2 module as above. Okay. So, this is something I am not doing, I expect you to do. So, now we will actually see some interesting construction of representations from old representations. So, that is actually going to give us many interesting way of creating representations, okay, from known representations. So, we already seen what is called this direct sum, okay. So, otherwise I will just recall. So, what is direct sum? So, if I give you two representation, let us say V1 and V2. So, given these two representation, now you can assume it to be this is just a G representation, not necessarily SL2 representation, okay, where G is Lie algebra. Now, given these two representation, we just want to construct what is this called this direct sum. So, the direct sum as a vector space, this is just all this Cartesian product. So, x is coming from V1 and y is coming from V2. Then the action of this G given to be, so you start with some element G in G, okay. So, then G of this x y is given to be just G x comma G y, okay. And I will leave it to you to check, this is actually defines action of G on V1 direct sum V2, and this makes what is called this direct sum, okay. So, direct sum of two G representation is again a G representation. So, this is not very hard to see. So, now we have what is called dual. So, this is very important concept, okay, dual representation. So, what is dual representation? Again you start with V, which is G representation. So, then we can construct this dual space which is home V comma C. So, all functionals from V to C. So, again you take it to be over complex numbers. So, what is this? This is set of all linear transformation from V to C. T is C linear. We know that this is a vector space. Now, what is given? G is acting on this capital V. Now, using this action, we are going to define action of G on this V star. So, how it is defined? You take x in G and then theta in V star. So, to define what is x dot theta, we need to tell how that x dot theta acts on some given element V in capital V. So, you take V in capital V. So, for all this data, then you define x dot theta to be just acting on V to be as follows minus theta x dot V, okay, and this is true for all x theta and V. So, now I will check, okay, this is the only thing I will check. This is going to give us actually representation, G representation. So, what we need to check? So, we need to check that this is actually linear in both these variables, okay. All those things I will actually leave it to you to check. So, basically what we have defined? We have defined this phi star, okay, from G to this GL of V star, okay, where phi is given to be G to GL of V. Then how we define this phi star? Phi star of x is acting on V star to V star, where x takes theta to phi star of x of theta is nothing but this x dot theta. So, this x dot theta defined to be x dot theta of V equal to minus theta of x dot V for all V in V. So, that is how we have defined, and this is, if you think about it, this is minus theta phi of x V, okay. So, now we want to verify this is indeed actually representation. For that we need to verify this phi is linear. So, I will leave it to you to check that. So, only non-trivial part we need to check it is a Lie homomorphism. So, for that you can see that why it is a linear Lie homomorphism. So, if you take this bracket x y and then act it on theta. So, we need to prove that this is exactly equal to x dot y dot theta minus y dot x dot theta. Okay. In other words, what is on the left hand side? Left hand side is bracket x y applied on theta and then you are just applying on some vector v. Then you get minus theta x y acting on this v. But this is because this bracket x y acting on v, that is actually representation. So, you get minus theta x dot y dot v minus y dot x dot v. Okay. And this is true for all v in v. So, that means what you are getting this is exactly equal to minus theta x dot y dot v plus theta y dot x dot v. Okay. This is what on the left hand side. So, we need to verify this is what you get on the right hand side. So, let us look at what is on the right hand side. So, you take x dot y dot theta. So, just take the first term, then apply it on v and then see what happens. X dot y dot theta applied on v, then it is going to give you. So, first you want to think this as some theta dash. Okay. So, basically you think like this, x dot theta dash on v, where theta dash is y dot theta. Okay. Because this is again a functional. So, then you can see that this is by definition this is minus theta dash x dot v. Okay. But you can go back and then see what is theta dash. Theta dash is y dot theta. So, that is going to give me minus y dot theta applied on this new element x dot v. So, then it is going to give me another minus. So, then this is minus. So, the minus minus will get cancelled, then theta y dot x dot v. So, the x dot y dot theta applied on v is going to give me this, okay, for all v in v. Similarly, if you compute y dot x dot theta applied on v, then you get first. So, you keep this y dot and then you take it to be that x dot inside. Sorry, you keep x dot, yeah, this is your theta dash. So, x dot theta minus y dot v. So, then the minus again another minus will pop up. So, that is going to cancel. So, theta of x dot y dot v. So, that is what you get. So, now what will be on the right hand side? So, that is the difference of these two. So, that is the difference of these two is theta of y dot x dot v minus theta of x dot y dot v. So, if you go back to the right hand side, so that is what we have, theta of y dot x dot v. So, that is the first term, and the second term is this minus theta x dot y dot v. So, that is what we have here. So, that proves left hand side is same as right hand side. Okay. So, that makes this phi star which we have defined is a Lie algebra homomorphism. So, that means V star is indeed representation for G. So, now we have another very interesting representation called tensor product. So, if you have not seen the concept of tensor product, I urge you to go and look at it. Okay. For example, Dumitton Foot will be a very good reference for tensor products. Okay. So, I am going to assume that you are all very familiar with the notion of tensor product, and I am going to just work with that assumption. So, what is tensor product? Okay. If I give you V and W, so these two are two G representations, then I can actually talk about this V tensor W over C. So, note that, so this will be span of over C all this what is called simple tensors, V tensor W, where V is coming from capital V and W is coming from capital W. Okay. And of course, tensor product is defined using some universal property and so on. So, I urge you to actually go back and then see what is that universal property and then how one can construct basis of this tensor product using the basis of capital V and capital W and so on, which I am not going to do in this course. So, now what we are going to do? We are going to actually define. So, these two are given to be G representation. So, we are going to define action of G on this V tensor W. How it is defined? So, you take X in G and then V in V and W in W. Okay. For this data, you just define X dot V tensor W to be, it is now defined using what is called this product rule, X V tensor W plus V tensor X W. Okay. So, now once you have defined this for simple tensors, then it is easy to extend this linearly to entire tensor product, okay, because any typical element will look like finite sum of these simple tensors. Okay. So, now it is easy to actually check this is actually indeed gives you G action on this V tensor W. So, maybe I will leave it to you to check. Okay. So, here is the checking part, check V tensor W over C is again G representation using this star. Okay. So, now we have another important space, okay, which is the home space. Okay. This is home of representations. So, this is again very important concept, but if you know dual and tensor, it is easy to actually get back home. Okay. There is no problem, but anyway let me define what is this home representation. So, let us say V and W, they are given to be two representations of G. Okay. So, then one can consider what is called this home space. So, that is set of all linear maps, okay, set of all linear maps from V to W, where T is C linear. So, again we know lots of information about this home space. Okay. So, for example, one can construct the basis of this home space using the basis of V and W. Okay. I will let you to think about all this. So, now how one going to define this action of G on this home V comma W using the action of G on V and W. So, that is defined as follows. So, if I take x dot theta, where x is coming from G and theta is coming from this home, okay, for all this. So, because theta is actually mapped from V to W, so I have to say that how it acts, this x dot theta acts on this capital V. So, for this data, what is x dot theta of V? So, that is given to me x dot theta of V, okay, because theta of V is an element of W, we have the action of x on theta of V. So, then you subtract theta of x dot V. So, that is your definition. Okay. So, this is your definition of this x dot theta that is acting on this V. So, if you take this definition, then I will encourage you to check that this home space is again becomes G representation. So, home V comma W is again G representation using this double star. Okay, at least once you should check these facts in your lifetime. Okay. So, these are all the facts, once you check and then you will never check again. So, I will urge you to check these facts. Okay. So, now we have this natural isomorphism between this V tensor W star and then home V comma W. So, note that these two spaces have same dimension, okay, because they have same dimension. So, if you are working with only 5 dimensional spaces, so then these spaces must be isomorphic as vector spaces, because dimension of both these spaces are the product of the dimension, because dimension of the dual is dimension of the space. So, the product actually is giving you the dimension. So, that means there is some isomorphism, but what I am saying, there is a natural isomorphism between these two. Okay. So, I actually kind of leave it to you to find out that natural isomorphism, and then using that natural isomorphism you can prove that. So, this is indeed isomorphic to. So, okay, the isomorphism should be like this. I will leave it to you to check this isomorphism indeed G module isomorphism if you start with V and W are G modules. So, this is G module isomorphism. Okay. For example, when W is C, then you get V star tensor C. So, which is isomorphic to V star. So, that is exactly equal to isomorphic to home V comma C. Okay, this is the way to remember where to put dual. So, this is again I will leave it as exercise. It is very interesting exercise. Once you figure out how to define the G action here, and because there is a G action here, you can see that indeed the G action of this home space coming from the G action of this V star tensor W, because you already have G action on V star and then you have defined G action on W. Now, using this natural isomorphism between these two spaces, one can define G action on this home V comma W. So, that is the action indeed we have defined here in this double star. Okay. So, that is all like direct computations you can actually do and then verify. So, I am not going to do. So, this is all like about general construction of modules from the known modules. Okay. Of course, you can always think about like various sub modules and then the quotient modules and so on. They are also some way of producing new modules from the given modules. Okay. So, once we have constructed all this, then we can ask this following natural questions for SL2. For example, so what you can do, so you can take this VD, okay, and then you can actually look at this dual. Okay. So, the very first exercise prove that this VD star is again irreducible. Okay. Because it is irreducible, so VD star must be isomorphic to some V of something. Okay. So, I just like let you to figure out what will be that something. Okay. This is going to be again some natural number, okay, and then you just figure out what should be that natural number, sorry, non-negative integer. So, the second question, so if once we have this tensor product, okay, so then it is immediately one can construct tensor product of two different irreducible modules. Okay. So, for example, you can take Vn tensor Vm for given n and m coming from Z plus. Okay. So, this is 5 dimensional representation of SL2C. So, the very first exercise you can prove that this is irreducible if and only if one of this n and m must be 0. Okay. So, this is irreducible if and only if the product is 0. So, indeed if you take n to be 0, then it corresponds to V 0, but V0 dimension will be d plus 1. So, 0 plus 1. So, it is one dimensional. So, it is isomorphic to just that complex numbers or the trivial module. So, if you take trivial module tensor with Vm, you will be getting actually the same module. Okay, this is inbuilt exercise. If you take Vm tensor with V0, then you get Vm again. This is true for all m. Okay, and it is not hard to see that V tensor W will be isomorphic to W tensor V as G representations. Okay. So, this is again I will leave it to you to think about, because what is the natural map? You can just take this simple tensor VW and then send it to the switch, okay, switching those elements W tensor V. Okay. So, this is actually even to get this map. Okay. So, this is you are going to define it on simple tensor, but you want to define this on the entire space. Okay. For that you can't just start with this map and then extend linearly to V tensor W, because the simple tensor they do not form a basis. Okay. They are just spanning set, and when you allow V W to be like any elements, then definitely you are over counting. So, definitely it will not become a basis. So, you have to think about how to make sense of this map, okay, that I will leave it to you to think about it. But this V tensor W is naturally isomorphic to W tensor V. So, now using this you can see that V of M tensor V of 0 is isomorphic to V of 0 tensor V of M, which is isomorphic to V of M. Okay. So, that is why whenever Nm and 0 you get this is irreducible. So, in all other cases when one of them are both of them are non-trivial, then we will never get it to be irreducible. Okay. Indeed, we have this very explicit formula to decompose this V of n tensor V of m. So, the formula is read as follows. So, if we decompose this, then this is isomorphic to, so V of m plus n direct sum etc. direct sum V of mod m minus n. Okay. So, each this V of m plus n etc. V of mod m minus n occur only once. Okay. The multiplicity of these modules are 1, and exactly these modules will occur in this tensor. Okay. This is actually very interesting exercise. So, one can do this in many ways. For example, one can do this at the level of character as well. We know what is the character of V of n. Character of V of n is nothing but x power n plus 1 minus x power minus n plus 1 divided by x minus x inverse. So, now what do? You just multiply these two and then try to actually group them together, then you will get what is on the right hand side. So, this is also you can write it as x power n plus etc. plus x power minus n. Basically, if you take okay, this is something I have not told, but anyway this is again another exercise you can take it to be. So, the character of V tensor W. So, like let us take VW to be just SL2 modules. The character as predicted, the character of V tensor W will be just the product of the character. So, that will be character of V times character of W. So, this is just a simple proof, because we are talking about only one eigen spaces corresponding to only one operator. For example, if you take this V tensor W gamma, so which is the gamma eigenspace, then you can see that this will be just a sum of all these eigenspaces V gamma dash tensor, okay, V gamma double dash, where gamma dash plus gamma double dash will be exactly gamma. So, in particularly the dimension of the space V tensor W gamma will be equal to summation dimension of this V gamma dash times dimension of V gamma double dash. So, indeed that is what you use in order to prove this product formula. Okay. So, check this and then using this you can get immediately this. Okay, I will stop here with this all exercises. So, unless you revise the notion of tensor products, so these exercises will become actually very difficult for you. So, I recommend you to actually revise the notion of tensor products and then using that you can do all these exercises. Okay. So, I will continue in the next lecture with the Gordan criteria for solvability and semi simplicity. So, those are very important concepts. Like I said, to prove those theorems, we need to actually revise what is called this Jordan-Chevalier decomposition. So, I will lecture on that, I will add it as appendix. Okay. You can actually go through that, not a problem. Thank you.